Our second speaker is Professor Ji Hui, who is the Associate Professor in the Department of Mathematics and the Institute of Data Science at National University of Singapore. He also served as the Director of the Center for Wavelet Approximation and Information Processing at NUS since 2014. His research interest covers computational harmonic analysis, computer vision, and machine learning. Today, he will talk about self-supervised deep learning for image recovery. It's your time, Hui.
All right, thanks Wenrei's introduction, and also thank the workshop organizers for the invitation, which gives me the opportunity to share some our recent works on deep learning. So today I will talk about supervised deep learning for image recovery. All right, this is a joint work with these three talented young people, Dr. Ji Hui from Southern China University of Technology, and Chen Mingqing also from South China University of Technology, and our research fellow Pang Tungyao from NUS. So let's see a few representative applications in image recovery. The first is a very basic one, image denoising. So you just write, you have a clean image X, then it's polluted by some noise, then you get a noisy one. So image denoising is then about how you're gonna get X from Y. That is how to remove noise N. Another one is image deblurring. So image blurring can be modeled by, you have a clear image, then it is convoluted with a smoothing kernel so as to lose the details. Then the image deblurring is about how you can recover a sharp image with all the details from an observed image, Y. Okay. Another one is image reconstruction in, for instance, in MRI, especially the CS-based MRI, the computer sensing. So basically, computer sensing means you just take a small percentage of measurement using some special designed sensing matrix, and hopefully using this small amount of sensed measurements, you try to reconstruct the whole image. Okay, it's called computer sensing. All these image recovery have a common character, that is, they can be formulated as a linear inverse problem in general. So you get a y equals to ax plus n. This a is a measurement matrix, okay, and n is not. So different image recovery problem will have different type of a. So easiest one is denoising. In this case, a is just identity. So it's actually a well-posed problem. And deblurring is because you're gonna have a convolutional matrix, which is determined by the smoothing kernel corresponding to a convolution, right? So therefore, it is air conditioned. And computer sensing is that you have the sensing matrix with far few measurements than the dimensionality of the image to recover. Therefore, it is a fat matrix with more columns than the rows. So it is air posed. Mathematically, you have an infinite number of solutions. So the main concern in the image recovery is then how you're going to suppress the noise magnification when you inverse this process. Another one is how to resolve the solution ambiguities if A is not invertible, like computer sensing. All right, so over the last 2 decades, regularization is actually one widely used technique. So the basic idea, you have to impose certain priors on the image you want to recover so that you can constrain the space of the solution. So basically, it can be formulated as an optimization problem with a regularization of functional, which is derived from the prior you imposed. So you have such a problem to solve. And in last decades, the most widely used, arguably, is piecewise smooth priors on image. That is, you assume the image can be modeled well by a piecewise smooth functions. Then, as a result, it implies that the most of local intensity variations, most local variations are 0 or close to 0. Here, I show you one demonstration that you have an image, then you take gradients on the horizontal and vertical, and you check its magnitude, you can see most are dark. Dark means it's just very small. This actually leads to the so-called sparsity regularizations using the so-called L1 LP norm to regularize the solutions. Therefore, you have an optimization problem with the regularization being LP norm of some coefficient that you apply some operators on the X. So different operators have been used to measure these local variations. For example, the most well-known is total variation. That is, you just assume using first-order difference operators to measure the local variations and minimize its L1 norm. Another one is popular is the wavelet transform based. That is, you measure this image using wavelet transform or frame transform, which is a redundant wavelet transform. And then you're going to have a bunch of filter bank to get the coefficient. Then you assume that the L1 norm of the coefficient of the image you want to recover is small. That is sparsity-based regularization. Well, of course, because you somehow design a transform to fit all the images, which usually is suboptimal for particular image, right? So a better way, I would say, is that you try to learn such a transform to specify the image for each instance. So which means a different image, you try to learn a different representation in terms of sparse approximations. So well-known work is the so-called sparsity-based digital learning, so KSVD method. So the idea is that you just take image, you treat the image as the collections of many small pieces. That is, you cut the whole image into small pieces, small matrices. Then you try to learn a dictionary so that under this dictionary, all the image patches can be sparsely approximated well. Okay. Another one is you learn the transform directly, the so-called data-driven wave type frame transform, which we did like 6 years ago. So the idea is that you just directly learn a wavelet transform, so you have a wavelet transform, and so that the corresponding coefficient is sparse. You constrain its L0 norm. This is actually so W is an operator which represents a wavelet tight frame transform. So which means you learn the transform so that under this transform, the image will be sparse. Then you can go back to using these regularizations, which is built on this sparse concept of the sparsity. All right, so this actually can be done directly on the noise image in the sense that it is unsupervised. Well, of course, if you go back, look at this problem, the resulting problem is non-convex. You have this term in the dictionary learning, and you have this term. So for the transform learning, you have this term and as well as this term. These terms are all non-convex. So of course, you cannot find in general, you cannot find a method that can solve it with global minimizer. Okay. Fortunately, we studied this problem and show that you can using the so-called proximal alternating iterative scheme. You can guarantee that at least you can find a critical point of the problem. So which partially address the issue about how to get a convergent algorithm. But of course, it's only partially addressed because it cannot guarantee you can find a global minimizer. But often in machine learning, you don't need to find the global minimizer because as long as you find a good one, it's sufficient. So here I show you the comparison about manually designed wavelet transform or frame transform and the transform learned from the image shown on the right side. So you can see the filter bank which learned from the particular image Lena, it actually captured all those kind of texture informations of image in comparison to the manually designed wavelet transform. Then you can see it indeed learned the pattern from image itself. Okay, continue. So we did this in like 5 years ago, but then actually right after 5 years before, okay. So deep learning actually emerged as one very powerful tool for many applications, including recovery. But here is that in the beginning, deep learning for image recovery is somehow does not do well. So the reason is that for the classification, you are trying to learn the mapping, which maps from the image space into a label space. Label space is very small. You only have a few finite number of labels, but image recovery asks you to learn the map from image to the image. So there's a big difference between image classification and the recovery because the mapping have different patterns. One is you just mapping from high dimension to a discrete, like finite space. The other one is you mapping from a very high dimensional space to very high dimensional space. Therefore, you need some special treatment where you try to using deep learning to solve these image recovery problems. Okay, I just mentioned a little bit. All right, so actually most deep learning methods for image recovery, current variables are supervised. Let's see the basic routine if you want to try to solve the image denoising problem. So that is you have collect many data, right? You have many pairs. That is a pair is that you have a clean image and its noise image. You make it have these many pairs. Then you start to train the network so that you can minimize loss functions. The loss function is relatively easy. It's just that you let the prediction from this network to approximate the ground truth image well. Very simple. And then once you have this model available, you just can do it using it to denoise the image. Just take it, denoise the image as input and just run it. All right. However, this routine for image denoising is usually not good if you use it for solving the general inverse problem, because as I said that if you do the deep learning for image recovery, you try to learn the map from a very high dimensional space to another very high dimensional space. Therefore, if you do the solving the general linear inverse problem the same way as image denoising, you don't use the model prior, because the model, you have the model A, right? It tells you how the image is degraded. So, okay. Secondly, as a result, actually, if you do that directly, you're going to have suffer severely from the overfitting. So a few years ago, then the people realized that a better way to develop a supervised learning method for solving inverse problem is build on some existing iterative scheme. So it's called optimization unrolling. So basically, just pick up some existing regularization model. Then you pick up some iterative solver for that. Then you have the iterative scheme. Every time you do the refinement, then you just replace those steps involve the regularization by a neural network, and then you're going to have a learnable regularization. That's a basic idea about optimization unrolling. So let's see some examples. If I just using pick up very simple one, I consider a total variation TV regularization, right? Then I consider a very classic method called half quadratic splitting scheme. So basically is that you're just introducing an auxiliary splitting variable z. Then you can split this solver into two steps. The first is use update x, then update z. And the first step, people call this inversion step, because you are using your model informations to get some estimation of xi. Another one is called the regularization method, because you introduce some priors, which is derived from here, to regularize, to fix the estimation of x, the current estimation. Okay, so simple then. If you want to introduce learnable priors, then you just replace this part, regularization step, by a learnable neural network. You are done. Okay, then you're gonna, this is so-called optimization unrolling scheme for constructing neural network for solving the inverse problem. Actually, this is a very popular choice. I think most current methods are built on such a scheme. The main difference is just choose what kind of iterative scheme. You have like ADMM and many others, right? Many others like splitting scheme, splitting method. but the idea is the same. So, but as we all know that these are the supervised learning methods. The key to the success, of course, including the develop the architectures, but the more importantly is probably is how to collect the data. So you need a comprehensive unbiased data set with a great amount of image pairs to train the network. Because remember, the network is about a mapping from very high dimensional space to very high dimensional space. So such a requirement on the data set will, of course, it will raise many practical issues, right? Because collecting training examples, especially collect the training examples with choose image. For example, if you try to do the image denoising, you have to collect image free of noise, okay? Then it's actually quite costly and not easy. And also, it's very subtle because for the medical image and the scientific image, the network trained using the data set might be biased because the data set itself might be biased. That is a concern. Another one is that because you're training the network on this provided data set. In other words, if you want to using this network to predict the new image with the structure which does not covered in the training examples, then you cannot do that. So in other words, this actually very unwelcomed in scientific imaging, right? We try to see the new things in scientific image. Okay, so of course there is a great practical values people try to relaxing this prerequisite on the data set when they try to using deep learning to solve their problems. Okay, so you can see that in the last 2 years, there is there is a rapid progress in a very fast pace, try to working on the unsupervised image denoising. So here I list the tables. So for example, the supervised method become somehow matured in 2017. Especially this DNCN is very representative work with good result. And then people start relaxing. 1 year later, or 2 years ago, 2 years ago, people start relaxing using the so-called weakly supervised. That is, you train the image pairs with both are not perfect, but they are the two noisy observations of the same image. We call this weakly supervised. And people also start to working on the unsupervised. That is, you have a data set, but you don't have choose on that. This is people so-called unsupervised learning. Of course, the most extreme case is that you don't assume you know anything else except the image you want to process. It is called self-supervised. So far, there is, 2 years ago, there is a very interesting work called DIP. I will cover this in a later discussion. So of course, if you consider general inverse problem, there's very slow progress on that because inverse problem in general is much harder than image denoising because it's ear post. All right, so of course, in this talk, I try to address the question is that if I consider a general inverse problem, how am I going to train a neural network to predict the truth from a degraded observation without seeing anything else? All right, that's the question I want to address. And the challenge you're going to have is that regularization. But this regularization is about how to regularize the network because you don't want to regularize the prediction. You want to regularize the network so that it can avoid overfitting. But meanwhile, you don't give up the learnability of the network, okay? Here I'll introduce two techniques, Here I will introduce two techniques we developed in last year. So one is so-called how to do the data augmentation to have a so-called self-supervised losing function. Another one is how to train a network with random process to approximate an MMSE estimators, minimum mean square error estimator. This is the solution we provide to answer the question. Okay, so let's see something very simple. Suppose I want to do the denoise image. Suppose I only have a noise image. So if your input is a noise image, the output you don't have choose, right? So still use a noise image. Then clearly you're gonna suffer from overfitting because you just do nothing. So the network just become an identity map. So input out prediction are both the noise image, right? You get zero cost. Of course, it's not what we want. So it is observed 2 years ago, some work so-called deep image prior, DIP. It shows that if you want to train the neural network, when you start to train the networks with iterations, the regular structure appear before the random noise. Okay, then this immediately give you a very nice regularization strategy, early stop. That is, you start to train the neural network. Then when, before the random noise appear, you stop it. Now, so the very classic early stopping actually can also be used here. Of course, this is rely on the assumption that regular structure appear before random noise. How this can be? Actually, this is related to the network structures. Actually, if we consider a CNN, convolutional neural network with encoder and decoders, because encoder will decrease the dimensionality. Encoder will decrease the dimensionality and decoder will increase the dimensionality. And to increase dimensionality, you can have involved the so-called upsampling, right? But how to do upsampling in the neural network? What you're going to do is you're going to use interpolation. For instance, linear interpolation. But we understand, right? If you do the linear interpolation, you assume the underlying function is smooth. So as a result, because of this interpolation scheme involved when you do the upsampling in the decoder, the low frequency that is corresponding to the regular pattern will appear before the high frequency pattern, which often is referred to the noise. That's one of the reasons why you have such deep image priors. One of the reasons, okay, I won't say all the reasons. One of the reasons is because you are using upsampling. Okay, so of course, this deep image prior does not solve the problem. So first is, even for the image denoising, the performance is actually not competitive. It cannot even beat the traditional well-established BM3D method, a very famous non-local method. And actually, the early stopping is easy in the classification, right? You have the validation data, you can check in when to stop. But if you do the unsupervised way for image denoising, you don't have choose. So when to stop, okay? So you have to stop right before the noise appear, but when to stop is a challenge, especially if you want to automate such a process. The second, for the general inverse problem, early stop cannot do the good job because for the general inverse problem, what we are worried about more is about the artifacts, right? When you magnify noise, you're going to have artifacts. These artifacts is also regular, it's not random. Early stop cannot avoid it. The second is that the priority is that the low frequency part showing before the high frequency part is not welcomed in certain applications. If you think about image deconvolution, right? That is, we are given a low frequency informations of image. I want to recover high frequencies. So for the image convolution, I will prefer give me the high frequency first. But that against that is not that early stop can do. Okay. So here, see, I will introduce the first technique. We try to do the unsupervised, self-supervised deep learning. So first question, because we don't have any choice, right? The first question you have to answer is that how to generate the data. So at least you can train a network. Okay, the basic idea is that we do the augmentation on the only input y. So synthesize a set of image pairs. So you have only a single y. I'm going to synthesize a set of y tilde. Then I define a loss function on this y tilde and y. Okay, so hopefully, in terms of expectation, they provide something related to the truth. So if you look at this one, suppose I can achieve this, what you have. So you define a self-supervised loss function on some data augmentation scheme, you're going to have such a loss functions. Compared to the supervised counterpart, it's weaker because first you have expectation, but the expectation usually is fine because this is expectation over all image pixels. You have millions of image pixels. It's not big deal. The big deal is that you have it only defined on the range of the A, which is make it weaker. All right, so now see how we do that. So here I show you two examples, how we're gonna synthesize YM. The basic idea is that you random select a subset, okay, of image pixels and replace its values or the damage its values. So one way to damage is just set to 0, okay. Another way is just to replace it by the average of its neighboring unselected pixels. Just replace the pixel which are chosen using the average of its neighbors. There are many ways to do that. Okay, I share two ways. So mathematically, then you can formulate as you consider one instance of the Bernoulli binary Bernoulli vectors. Okay, you have this bi. Then you define it on this. This one will replace certain pixel value into 0, right? Then you do for those set to with those pixel, you do some operations. This actually is the general mathematical models for the two example data augmentation we talk about here. Okay, now we're ready. So now we define the loss function by such. Okay, you're gonna have these Bernoulli vectors multiply here, and you can prove that suppose I consider random noise, IID random noise with 0 mean. Then the expectation of all these like Bernoulli variables and the noise indeed is exactly this form, a weak form of the supervised version. So when A is identity, which refers to the image case of image denoising, this indeed give you a supervised. In terms of expectation, it give you a supervised loss function. Okay, that's a very good news. So here I show you what exactly we are doing here. So that is, if I consider a noisy image Y, right? What I did, I first damage certain pixels. Here you can see those black spot. The things are damaged. This is the things are not damaged. All right. Then what this loss function is doing is that you actually using these undamaged image pixels to predict damaged image pixels and measuring its prediction errors. That's how it is. That is, you just random select a subset using the select one to predict unselected one or vice versa. That's how it is. Okay, so recap. We partially address the problem. At least we know how to train the network, okay? That is using the data augmentation we did and the self-supervised loss function we defined. We actually try to train the neural network with such a cost function in some sense. And of course, it does not solve the problem completely because you still have two issues. The first is for the general A, this prediction error is only defined on the range of A. So suppose A is not full rank, you get a problem, and you're gonna have solution ambiguity still. You still have solution ambiguity, and another issue is that you only have one sample, okay? Because you only have one X, you don't have many X, so you're gonna have large variance. So we need more regularizations. How to do it? Well, we actually check again and try to find the recipe in the Bayesian inferences. We try to approximate the MMSE estimators, all right, by using a network with random process. So this is a quite a classic way how to do the Bayesian inference. So basically, suppose my network is powerful enough, it is actually can generate X, right? Then you're gonna have replace this X by these generators. You have such a definition for the MMSE estimators. Of course, the posterior distribution here is not variables, right? So what the Bayesian inference doing is that you approximate this posterior diffusion by attractable diffusion. We call it Q. Okay, then what you're going to do is that you're going to construct an estimator by minimizing the KL divergence between the true posterior diffusion by this tractable diffusion. Once you're done, you get an approximate MMSE estimators. Then you get a prediction, which of course is not MSE, but is approximate MSE estimation. Okay, so here I consider two Bayesian approximations. So one is dropout. It's actually widely used in deep learning. So dropout, it means that your weight follows is somehow like a Bernoulli variables. So you have beta. Beta is the weight. You have the theta I, which is the weight, and it multiply a binary Bernoulli vector. So you have chance this weight will be not used or used. That is actually the dropout. Actually, we show that for such kind of, if you use a dropout network, then you can show that the Ki divergence indeed is a very trivial one. It's just a classic like fidelity term. Or you can also using the Bayesian network with Gaussian process. That is, every weight of the network follows is a random variables follow normal distributions. Then you have two parameters. One is variance. One is one is mean. One is variance. Then in this case, actually we have that the KL divergence indeed is the same as that. You still have standard fidelity term, but you have two additional regularization on the parameters of the distribution, which is a expectation and a variance, together with this negative log, summation of log. So if you use a Gaussian neural network, you're going to have this additional regularization. So then, okay, then this is how you done, right? Then if you are using this Bayesian network with random process, so you just start to train the network by minimizing its Ki divergence. Once you are done, then you start to run the test. So remember, the test is mathematically it should be this one, this integration. Therefore, we just using Monte Carlo approximation, the standard procedures. You generate KT instance network from the chain Bayesian network. Then you generate total, sorry, this should be T. You generate the T predictions and take the average. That gives you an approximate MME estimation. Looks like quite simple. Well, indeed, if you look at, it looks like if you look at this, so I have to clarify. If you look at this dropout, it looks like you did nothing special, right? However, in terms of machine learning, this process is very different from the optimization unrolling scheme I introduced for supervised learning. Because if you think this in terms of example learning means you are using multiple simple model to help each other to produce accurate prediction. So indeed, the optimization unrolling scheme is actually related to the boosting scheme. That is, you just introducing simple model gradually, one by one, every time you try to refine it, okay? But this is only doable if you have choose, right? Because you try to refine the estimation every time using a simple model. You need guardians, and these guardians have to come from the choose, okay? However, for the self-supervised case, we don't have any samples available. We don't have any choose to take a look at it. So what you can do is probably, okay, I'm not only can do, but probably a good choice is using boosting. That is, you just synthesize multiple simple models which produce not so good estimation. However, you can take average. Hopefully, this model average can help you to reduce the variance. Okay, that's the difference between supervised learning and unsupervised learning. So let's see how to use these two techniques we introduced to solve the real problem. So first is we consider image denoising, right? So we are using a dropout neural network with an encoder-decoder structure. We have 6 encoder blocks, 5 decoder blocks, and we will try to do the image denoising to improve its signal-to-noise ratio. So this is how you do. Remember, here we are using two things together: the self-supervised loss function together with the approximate MNC estimator. So therefore, this is the loss function we're going to use. Okay, so you have two random things. One is y tilde m, which is done by the data augmentation, and you have this. All right, and you have sorry, here I forgot you have another one, c. This c is a dropout. This c is a dropout variable. Then you just using dropout, train the network with dropout to do these Bayesian inferences. You find the parameters, this theta I. Because this dropout rate is fixed to 0.3. Once you're done, this is the final loss function you're going to use. You have two Bernoulli vectors. One is to do the data augmentation. The other one is to do the dropout. So let's see some result. Here you can see if we compare this because our method does not call any training samples, right? So we compare, for example, KSVD and this data-driven wave type frame and the well-known BM3D and another this self-supervised method. You clearly can see our method is much better than existing solution, unsupervised solution, DIP, but it even has the edge over the very famous BM3D method, and it's definitely way better than the KSVD method. All right, we consider this on the two data set with different signal-to-noise ratio. So if you compare with different type of the supervised learning method, for example, this DN-CN is a very representative supervised learning method, and this N2N is weakly supervised. This N2V and N2S are two unsupervised methods. We still have the edge over this method on the set 9, but we are doing slightly worse than the supervised method, DNCNN, with 0.3 gap in this particular data set. I will say this is reasonable because they are using training data to turn up the network, and our network cannot see anything else except the data for process. Okay. So this is the result on the real world image denoising. Actually, we can see our performance is comparable to the supervised method. This is, I think, is considered very promising. We don't using any training samples. We can achieve a similar performance. All right, but one issue is that computer cost, because you have to train the network, all right, for each particular image, which make it somehow slow. So this is computational cost. If you want to process an image size to 200 times 200, then it takes around 1 hour to finish the whole training and the testing. That's a cost. So here I show you whether, because the idea is that somehow more like example learning, right? You are using multi-base model to get a prediction, then you average them out. So you can see here, what I show you, I give you the result on the two random image. Every time I show you how, if you use the predictions from different instances, how this average out will improve performance. So you can see it can gradually get more and more performance, but after, I would say, after 20, it more or less become flatter. So in other words, these prediction indeed help to each other. The average will more like to reduce the variance. Okay. So this is for the image deep learning. We are using the same network architectures, but we are using different way to do the dropout. Every layers we're gonna increase dropout rate by 7.5%. For the decoder, we're going to decrease by the same amount between consecutive two blocks. And then we're still using the self-supervised lose function together with the dropout. And then so this will be the lose function. And again, we do all the way the same as we did for the image denoising. And this is the resulting cost function to minimize. Okay, so this is experimental setup. We consider 2 image data set and 8 motion kernels from a paper. And you can see the result. Actually, if you compare to the non-learning method and the supervised learning method, our method has clearly performance advantage over existing data-free. I will call this data-free method. Okay, I'm running short of time, so I will do quicker. So therefore, for the supervised method, we actually provide comparable performance to most existing supervised one. Okay. This again, here I show you whether your prediction from multiple instance networks will actually help to reduce variance. Here is a 2D visualization using PCA, and this again the same graph, and you can see the average over multiple prediction will reduce the variance and help to improve the performance. All right, I have 5 minutes left. I will have last application. This application is actually quite surprising. That is, suppose I consider CS, the computer sensing, in MRI, because you know that MRI is slow. The less measurements you collect, you're gonna reduce the time to take the image. So basically, the computer sensing means I take some measurement, only a small portion of the measurement, for like 10% of the measurement using some sensing matrix. Then I try to reconstruct the image. In this case, the A is actually severely underdetermined. You have like 10 unknowns. You have the unknown which are 10 times than the equation you have. Here, I only consider a decoder without using the encoder. There's a reason for that. Because the computer sensing, the measurements is somehow taken from applying a somehow random Gaussian matrix on the image. So the measurement itself seems like highly decorrelated with each other. So we don't do such treatment on the data augmentation. We only do the one technique, that is train the network with Gaussian process to do this inference. And so this, because I have a decoder network with each weight follows normal distribution. Then you have a cost functions. So remember, for the Gaussian Bayesian network, you have additional regularizations on the parameters, which is the expectation and the variance of the normal distribution. So in comparison, I will show you. So suppose I do this scheme. In comparison, I do a deterministic network. So I use either I don't use any regularization on the weight, or I using the most like trivial, just using the L2 norm square regularization on the weight, like L2 norm square decay on that. So you can see this trivial regularization does not do the job well. You have a large performance decrease. Okay, so in some sense that this most widely seen regularization for the network does not really do the job, but ours actually much better than that. So this is the result which actually amazed me a little bit. So I consider 3 sampling masks, 1D, 2D Gaussian, and a radio. And I compare those non-linear, this is a classical method, total variation, and analytic method. And these 3 are the supervised learning method. These 2 using the GAN, another famous technique to do this kind of unsupervised case, and the DIP. So you can see it's actually very interesting to see both the 2 self-supervised methods did a better job than supervised case. Okay, that's quite interesting. And clearly you can see, suppose I consider the ADM net, which is actually using the optimization unrolling using the ADMM method. So you can see we have a large performance gain over it. And the thing is that they are trained using the truth, but we don't see any truth. So that's kind of very interesting phenomena that for this sensing, the self-supervised method even do a better job than supervised learning method. So here is the visualization of something. You can see our method actually produces very nice reconstruct images in comparison to the others. All right, so I think, yeah, I will finish it in 1 minute. So here I introduced two techniques. We try to do this thing, how to do the self-supervised learning for solving the image recovery problem. Okay, two techniques we introduced. One is how to design a self-supervised loss function from like nowhere. Okay, using this random sampling-based data augmentation. And the one is how to using this network with random process to do the approximate MS estimator for the image recovery. And the performance is that without seeing any training examples, we actually have better performance than those unsupervised or regularization method with not core training examples. Actually, is actually comparable to those supervised solution, which requires the training examples with the truth. Of course, the works we did is kind of like more in terms of try out. We find this phenomena, how to do the things, but we really have no good understanding of the mathematics behind. We still try to figure out why it works well, okay? And we still hopefully we can provide some better understanding in future. Also, we also interested in how to develop new regularizing strategy to regularize the network, but not regularize the prediction. That requires a very fundamental new idea about how to think about regularization. This will be our future work. Okay, I will stop. Okay, these are the references we have. So 2 works are published and 1 work is under review. So we have already the code and the model at GitHub for the noise to noise, but the other one we will put online shortly. Okay, that's all I want to say today. Thank you. And any question?
Good, very nice talk. Let's have a Q&A. Jin Chao just left me a message on the chat box. He has some questions. Jin Chao, why don't you ask directly?
Well, it's a great talk, and I'm very impressed that this unsupervised learning is very competitive for the denoising. You actually, that's quite remarkable. You actually made a comment at the end of your talk. What is the mathematical reason why this would work? I've been thinking about. Let me give some shot.
Okay.
So, if you think about this denoising, the traditional CNN with the ground truth, you do supervised learning, and of course you have a reasonably good results here. Here, you don't know the ground truth. You just have noise data.
Yeah.
Then you just say, as you said in the very earlier, that basically the identity map is your global minimizer. So
yes.
you don't get anything. But the thing is that, of course, then you do the unrolling, you do this optimization algorithm. This optimization, it depends, you're really effectively adding a regularization term there. For example, use a SGD method. SGD method, even the deep learning in general, you don't have to put a formally a regularization term there in the loss function. But nevertheless, if you do the gradient descent, stochastic gradient descent method, that increase the smoothing effect there. And then, so there's one factor that is because of this stochastic gradient descent method has this regularization effect. Now, and also, even though you're talking about early stopping, even you don't stop early, you never converge anyway, because
actually, I made a comment for the image noise.
Unless you let the learning rate go to 0, but even for convex problem. But anyway, all the training algorithm are early stopping. You always stop somewhere.
Yes,
So,
yes.
So this is one of the mathematical. I'm trying to.
Yeah, good. Yeah. Actually,
implicitly either regularization there. Okay, there's another one you can think of the following. The way to check whether that is true or not, you replace the stochastic gradient descent method by the fully gradient descent method. See if you can get the same effect.
I see.
Not the denoising effect, because the convolutional neural network, you do this cosine, what I call multi-grid, you do the cosine, and then you do pooling. Yes. In this procedure, you get all your, the image go to the cos mesh, the low resolution mesh. This is a filtering process, get rid of some kind of noise, which is usually in the form of high frequency. And then you go back. You do first encoding, right? Encoding you throw out. It depends how you train this, and when you go to the cosmos, some noise get rid of it. So you go back. So one way, I guess I'm quite trying to say is that whether this cosine procedure, pooling procedure will contribute to your unsupervised learning there. One way to check is that what if you replace CNN by a fully connected deep neural network, one layer? See if you get the same effect. Because I think the CNN, I'm a multi-grid guy. If you do a CNN, it's really a multi-grid algorithm. Multi-grid is going to cos mesh the low frequency. You cannot see noise in the, at least the high frequency in the cos mesh or low resolution images. So collectively, that you have the at least the two factors that I'm just thinking of the mathematics because you mentioned that. And is the training algorithm has a regularization effect. There's a multi-grid structure in the CNN has also a filtering process. One of the things I want to comment is also depend on what kind of the activation function you choose. I would assume you use ReLU when you do the CNN.
Actually, we did not actually use any specific architecture. We just, because our goal is not on the study of architecture, we just pick up some very a vanilla version of encoder decoder.
So you didn't do any particular CNN?
No, we don't. We actually also tried the ResNet. It actually has a similar result. So yeah.
Only one layer.
No, the ResNet is you have the jumping.
It's a CNN ResNet.
Yeah, CNN ResNet. Actually, we also can have the similar result.
Try the resonate without pooling. So what happens?
No, you're right. We don't. Actually, that's interesting. That in many image recovery, usually people don't using pooling.
Well, in the denoising things that the way I did some experiment myself.
So I see.
You do the encoding. You do encoding with CNN, but usually when you do the CNN for the image classification, there's no decoding part. You can add the decoding part to get back to the original image, which is your denoised image. But anyway, during this process, there's a denoising process which is contributed by both the regularization provided by the stochastic gradient descent type of method, which has a regularization effect, and also the cosine also somehow has some noise and filtering process. I'm just trying to.
I agree. Actually, I particularly regarding your first comments. Actually, what we did is this augmentation, loss function. Eventually, is try to think about how to design the gradient so that it can guide to the mapping I want. But we have no idea. We have no motivations on how to modify this. How to design this gradient so that it can converge to the mapping I want. That's why we just using the loss function together, try to get some intuitive way so that it can influence the gradient. I agree with you that for this deep learning, the gradient is essential.
But you manage to tune your system such a way to obtain remarkable result. That's really very impressive. You actually said that is even better than the supervised learning with the graph.
Yeah, this is the interesting that in the comparative sensing, if you look at comparative sensing, this is a typical inverse problem. We actually both one is using DIP, so using early stopping, and ours both actually are better than those supervised case.
That's very nice.
Yeah.
Thank you.
Thank you.
Is there any other questions?
Yeah, any other question?
I have one.
Sure, go ahead.
So you basically show in one slide that your self-supervised cost function is a consistent estimator for your unsupervised cost functions, right? Under the expectation, they actually commute. So I think this slide.
Yes, I think I have here, yeah.
So to have this, what is the assumptions on the noise? You know,
We assume the noise is independent. That's the key. The key is the noise, it has zero mean. But noise has zero mean is somehow a common assumption. But we assume that for every image pixel, the noise is independent from each other. That's the key assumption you have to make.
okay, thank you.
Yeah.
Okay. Any other questions?
If no other, I'm just this is a very interesting talk. You have a page where you say you have a Bellori distribution, then you take the expectation. Somehow you get the ground truth. I don't quite get how do you get that? And
which one I get a ground truth? You mean this self-supervised?
Go previous one. Go to previous page. Now there's a from Y you can get an X. No, not this one. Oh yeah, the result that. Yeah, why don't the left go to the right? Why is the noise the data, right?
Because yeah, it's the noise data. So why contain the noise? What you need, because
well, you don't know what the noise is. How do you get it out?
Okay, actually, the key idea lies here. Remember, why contains the noise?
Yeah.
Okay. So, but this you cannot just spin out because the noise here will be correlated to this. Okay. So the idea is that this you throw away pixels and using the remaining things, which actually make these two things, the noise will be decorate to each other. Then when you take square,
unless you know exactly the distribution of the noise, how can you do that? I'm sorry, I just don't quite get it.
No, because this noise and this noise here and this noise here will be independent. Then you spin them out. When you take expectation, it will be zero. Only thing left is the variance of the noise. But the variance of the noise is a constant, somehow a constant which does not affect your result.
Okay.
So to put it this way is that probably I probably is a bit did not write carefully. A better choice is to this one plus a constant. This is related to the variance of the noise. I will use like equivalent is better. Yeah.
Okay.
So we have another question in the Q&A. Someone's asking, did you consider finding a way to combine supervised and self-supervised learning by incorporating available?
Very good question. Actually, there is so-called, I don't know, one idea is probably related to the Bingdong talk about, okay, just quick to my mind, probably to Dongbing said meta-learning. So basically, one of the way to do that is you first train a very like generative, very general model on a large data set. Then when you try to process a particular image, you take another round of the training, but using the gradient from that data you want to process. That's one way. So basically you have some pre-trained model, very big. Then when you have a new data comes in, you modify this model using the gradient, which introduced by this new data to do some further like refinement on the general model so that it can fit the particular instance of the new data. Right? That's one way, is a very quick way to combine the supervised and unsupervised.
Okay, good. We have to finish.
Okay, sorry.
So yeah. Thank you for very.
If you have question, just email me. Yeah, I will have to answer.
yeah, it's a very nice talk, and also it's a very productive discussion. So then we switch.
I will stop the share.